Welcome viewers. We are starting series of lectures on linear algebra. This is the first lecture in this series. In this we will be discussing vector spaces. Viewers, we are performing operations of additions and multiplication on numbers, but they are performed on vectors as well. We have seen how addition and scalar multiplication is performed on matrices. They can be performed on polynomials also. Similarly, the linear combination of objects appear in many different contexts, like we can have linear combination of vectors, solution of differential equations. Now, a branch of mathematics dealing with the common properties of sets and linear combination of its elements is linear algebra. We start with the definition of vector spaces. Now, vector spaces, sometimes we call it as linear spaces, consist of the following. The first is the set of real numbers, we call them scalars, a non-empty set V of objects or vectors, and two operations defined on them, plus and star. They are defined as, plus is defined on set of vectors. So, if we have a pair of alpha and beta in V, then another vector alpha plus beta is also in V. We say alpha beta is the sum of two vectors alpha and beta, and if this is also in V, then we say vector addition is satisfying the closure property, or we say vector addition is closed in V. Now, this vector addition must satisfy following axioms. The first axiom is that addition is commutative. That means if we add beta in alpha, that is alpha plus beta, or we add alpha in beta, that is beta plus alpha, it is same for all alpha beta in V. That is alpha plus beta is equal to beta plus alpha for all alpha beta in V. If this property is satisfied, then we say addition is commutative. The second axiom is that addition is associative. By this we mean to say that if there are three vectors alpha, beta and gamma, then alpha plus beta plus gamma is equal to alpha plus beta added, and then we add gamma into it. So, we will have alpha plus beta plus gamma is equal to alpha plus beta, and then we add gamma to it. That means it does not make difference whether we add beta plus gamma first and then add alpha into it, or we add alpha plus beta first and then add gamma. In fact, this means these brackets are meaningless. We can ignore them. So, if this property of addition is satisfied, then we say addition is associative. The third axiom is that there exists an additive identity in the set V. By this I mean to say that there exists a member, call it 0, in V such that alpha plus V is equal to alpha. That means whenever we add 0, whenever we add anything on 0, that thing remains the same, that is alpha plus 0 is equal to alpha for all alpha belonging to V. Such a vector is called additive identity in V. Then the next axiom is that additive inverse exists for any number, any vector alpha in V. By this I mean to say that for given alpha there exists another vector, I call it minus alpha, so that alpha plus minus alpha is equal to additive identity null. So, alpha plus minus alpha is equal to 0, or we say minus alpha is the additive inverse of alpha. Similarly, scalar multiplication also has to satisfy certain properties. First thing is the closure property. By this I mean to say that if there is a scalar C in set of real numbers R and a vector alpha in V, then the vector C star alpha is called the scalar product of C and alpha. And if C star alpha is a vector and it is also in V, then we say it satisfies the closure property. So scalar multiplication satisfies the closure property, means that C star alpha is also in V for any given scalar C. It has to satisfy other axioms, we call it A5. It means C star alpha plus beta is equal to C star alpha plus C star beta for given alpha beta in V and C in R. By this I mean to say is that you add alpha plus beta, two vectors, and then multiply it by the scalar C. This amounts to be the same thing as if we have multiplied alpha with C and beta with C. So this is a scalar multiplication. We add the two vectors and what we have is another vector which is the same as C star alpha plus beta. Now this property is called that multiplication by scalar is distributive. So this is scalar multiplication and this is addition. So this scalar multiplication distributes the addition of vectors. That is why it is a distributive property of scalar multiplication. Next is C1 plus C2, two scalars, when they are added and then multiplied by a vector alpha, then this amounts to C1 star alpha plus C2 star alpha for all alpha in V and C1 C2 in R. We say that multiplication by vectors is distributive with respect to scalar addition. So this alpha, when multiplied by these two, addition of two scalars, then it is distributed as C1 star alpha plus C2 star alpha. The next is the associative property. Here we will have C1 dot C2, that is multiplication of two scalars multiplied by a vector alpha is equal to C1 star C2 star alpha. Now here you may notice that this dot simply means multiplication of two scalars, simple multiplication of two scalars. So when the two scalars are multiplied, we will be getting another scalar. Now when this scalar is multiplied by vector alpha, then what we have is C1 star C2 star alpha. That means this is equal to C2 is multiplied by C2 scalar is multiplied by vector alpha. This becomes a vector, and then when this vector is multiplied by the scalar C1, then we will have C1 star C2 star alpha. So this is a sort of associative property. So multiplication by scalars is associative. Last property is multiplicative identity, that if there exists one in R such that 1 star alpha is equal to alpha for all alpha in V. So there has to be a scalar 1 in R which when multiplied by alpha remains unchanged. So this property has to be there, and when all these properties are satisfied from A1 to A8, then we say that we have a vector space. Now we say that unless the vector addition and scalar multiplication is defined, we can't say that whether a given set V forms a vector space or not. That means to define a vector space, we have to have a set V of vectors and two operations, the vector addition and scalar multiplication. Now with this, if we include the closure property of vector addition and scalar multiplication also, then this triplet V plus and star is a vector space provided all the 10 properties are satisfied. These 10 properties are two closure properties, one with respect to addition, another with respect to scalar multiplication, and 8 axioms which I have just now discussed from A1 to A8. Now let me explain this with the help of an example. So let us consider the set of vectors in two-dimensional plane R2. So V is a set of vectors where alpha is a vector in R2. So it has to be an ordered pair x1 comma x2, where x1 and x2 are real numbers. So if we consider this set of vectors and we define the addition of two vectors alpha x1 comma y1 and beta x2 comma y2 as another vector gamma, which is x1 plus x2 and y1 plus y2. So, if we define this way, then vector addition is closed, and we also define the scalar multiplication of vectors x1 y1 with scalar c as c star x1 comma x2 as cx1 comma cx2. Both the components of the vector are multiplied by c. Now this is a real number, this is a real number, it's again a pair, so this also belongs to V, and that means scalar multiplication, if we define in this particular way, is also closed, or closure property is satisfied by scalar multiplication. Now we have to check whether all the other axioms A1 to A8 are satisfied or not. So to start with, we first consider A1, which means addition is commutative. So to check this, we consider two vectors. First is x1 comma y1 and the second is x2 comma y2. By definition, the way we have defined vector addition, it is x1 plus x2 comma y1 plus y2. But x1, x2, y1 and y2 being real numbers, their sum is also real numbers. So x1 plus x2 and y1 plus y2 can be written as x2 plus x1 and y2 plus y1. Now here one may notice that this plus here and this plus here, that means plus on the left hand side and plus on the right hand side has different meanings. Here the plus means we are adding two vectors, so it is between two vectors. So this plus means vector addition, while this plus means simply we are adding two numbers. So this plus refers to addition of two real numbers. So this is a real number, this is a real number, that is why we can write it as x2 plus x1 and y2 plus y1, and by definition this is equal to x2 comma y2 plus x1 comma y1, and that simply means x1 y1 plus x2 y2 is the same as x2 y2 plus x1 y1. That means order of addition of vectors doesn't make much difference whether we add x2 on in x1, whether we add this vector in this vector or this in this, it is one and the same. So we say that addition is commutative. So the next property is the associative property. So if we consider three vectors now, alpha, beta, gamma as x1 y1, x2 y2 and x3 y3 respectively, then this sum is given by this pair, and this can be simplified further. This second bracket can be simplified to x2 plus x3 and y2 plus y3, and then you can add this vector here. So it is x1 plus x2 plus x3 comma y1 plus y2 plus y3, and since x1, x2, x3 are simply numbers, so they can be associative. So you can change the order of bracket. So that simply means x1 plus x2 and then add x3 in this same way, y1 plus y2 and then add y3, and further simplification will give us x1 plus y1 plus x2 plus y2 plus x3 y3. So order is not important, and what we have finally is alpha plus beta plus gamma. So associative property is satisfied by vector addition. So first two properties being satisfied, let us check the third property, that is additive identity. So in this set of vectors we say theta is equal to 0 comma 0, where both the components are 0. They belong to V because they are real numbers. So V is additive identity and it belongs to V. Let us check that it is additive identity or not. For this, consider any vector alpha, add theta into it, and what we have is x1 comma x2 plus 0 comma 0, and it amounts to be the same vector as alpha. So we can say that there exists additive identity theta. The next property is additive inverse. So for given vectors alpha, x1 and x2, there exists minus x1 and minus x2 in V, such that x1 plus x2 plus minus x1 comma minus x2 is equal to 0 comma 0, and this is nothing but theta. So x1 plus x2, for given x1 x2 we have minus x1 minus x2 in V, it is in V because x1 and x2 are numbers, and if x1 x2 belongs to R, minus x1 minus x2 also belongs to R. So inverse of x1 x2 is minus x1 comma minus x2. So for given vector alpha there exists its inverse. So this way additive inverse exists in V for all alpha given in V. Now comes the scalar multiplication. We first check the distributive property. So C star alpha plus beta is equal to C star x1 comma y1, that is alpha, plus x2 comma y2. We can add the two, it is x1 plus x2 comma y1 plus y2 multiplied by C, and then by the definition of scalar multiplication C can be taken inside. So it is Cx1 plus x2 comma C y1 plus y2. Then you can simplify this because C is a scalar and x1 x2 are real numbers. So we can write it as Cx1 plus Cx2 comma Cy1 plus Cy2. Then this is nothing but Cx1 comma Cy2 plus Cx2 comma Cy2, and by definition of scalar multiplication we can say it is C star x1 y1 plus C star x2 y2. Finally it is nothing but C star alpha plus C star beta, and this is, we have started with C star alpha plus beta and finally we arrived at this result, and this proves that scalar multiplication is distributive over vector addition. So this is the next axiom. Then A6 means scalar addition star the vector xy. So it is C1 plus C2x comma C1 plus C2y by the definition of scalar multiplication, and then of course these are simply numbers as we are doing again and again. So they can be simply multiplied, and then we finally have C1 star x comma y plus C2 star x comma y. So the property A6 is also verified for this class. Then next is A7, which is the associative property. So it is C1 C2 multiplied by alpha. So we have C1 C2 star, alpha is x comma y. So we say C1 dot C2 multiplied by x comma C1 C2 multiplied by y. So this is the vector, and then we again apply the associative property for real numbers, and it is C1 dot C2x. So we can change the order here, the bracket has been changed, same thing will be done here, and then C1 can be taken outside, and what we have is C2x comma C2y. This is nothing but C1 star C2 star x comma y, and finally what we have is C1 star C2 star alpha. So we have proved that C1 dot C2 star alpha is the same as C1 star C2 star alpha. So the last property is multiplicative identity. So we have to prove that there exists a scalar 1 in R which when operated upon the vector alpha it remains the same. So to check this we say 1 is that multiplicative identity. So 1 star alpha is equal to 1 star x comma y. We apply the multiplicative definition of scalar multiplication. It is 1 dot x comma 1 dot y, which is nothing but x comma y. So this is the same as alpha. So finally what we have is 1 star alpha is equal to alpha. So this 1 is such a multiplicative identity. So there exists a multiplicative identity 1 in R. So all the properties are satisfied. So one can say that R2, that is the set of vectors in R2 plus the vector addition star the scalar multiplication is a vector space. So to check that a given set and the two operations defined on them on this particular set is a vector space, you have to prove all the properties, and in this particular case we have shown that all these properties are satisfied. So R2 plus star is a vector space. Now this is one simple example. I'll extend this simple example to Rn. That means we have earlier taken as two-dimensional vector space. Now we are taking n-dimensional vector. So we'll have V. The set V is consisting of pair of n real numbers. So, it is x1, x2, xn, where all these belongs to R. Then this is a vector space in Rn with respect to vector addition. So, how we define vector addition in this? This is the vector addition. We will have x1, x2, xn plus y1, y2, yn is equal to x1 plus y1, x2 added into the second component, x3 added into the third component, xn added into last component yn. So, that is how we define vector addition. Then how we define scalar multiplication on this set? So, if we have a scalar c, when c is multiplied with this vector, then every component is scaled by c. So, it is c star x1, x2, xn is cx1, cx2, cxn. So, if we define scalar addition in this way and scalar multiplication in this way, then one can very easily check that this is also a vector in V, this is also a vector in V. So, addition is closed and scalar multiplication is closed. One can very easily check all other properties A1 to A8 for this set, and one can prove that this is also a vector space. So, closure we have checked, commutative property you have to see, this will always be satisfied because these numbers x1, x2, xn etc. these are real numbers. So, as we have proved in earlier example, this will also be proved in the same very manner. So, closure property, commutative property, associative property, all the distributive properties are satisfied. Only thing is you have to show that there exists a zero vector in Rn. So, we say that zero vector is nothing but where all the components are 0. So, if this is the zero vector, then one can also find additive inverse for all x1, x2, xn. So, inverse also exists. Similarly, scalar 1 is also there, which when multiplied by the given vector x1, x2, xn will remain unchanged. So, this is also a vector space. So, V defined in this manner, addition in this particular manner, scalar multiplication in this manner is also defines a vector space. The third definition is, third example is the set of m by n matrices. They also form a vector space over matrix addition and scalar multiplication of matrices. Now, to prove this, one can say that addition of matrices is closed, because if we are given two m by n matrices, then the result is also the sum of two m by n matrices also an m by n matrix. So, it is closed. Similarly, when you multiply a scalar c to a matrix which is of order m by n, the result is also an m by n matrix. So, this is also closed. So, the two operations are closed in the set of matrices. Then comes other properties like, but these are already been established, that matrix addition is commutative, matrix addition is associative. One can say that theta or the null matrix of order m by n is the additive identity. Now, the next is the additive inverse. So, for a given m by n matrix AMN, the additive inverse is minus AMN. This always belongs to the given set of m by n matrices. So, this is also defined. The next is A5, that is scalar multiplication distributive over vector addition. So, we consider ijth element of m by n matrix A, and Bij is the ijth element of m by n matrix B. So, when C is multiplied with this, let us see what will happen. C multiplied by Aij plus Bij's, when we add two matrices, they are being done element wise. So, ijth element of A and ijth element of B matrix will be added together, giving us Aij plus Bij of the m by n matrix. So, this is scalar multiplied by C. So, this simply means C times Aij plus C times Bij of m by n matrix, and then one can split the two. It is Caij m by n plus Cbij m by n, and that simply means Ca plus Cb. So what we have is C star A plus B is equal to Ca plus Cb. So this property is also valid for m by n matrices. Now comes the next distributive property. So we have two scalars C1 and C2. They are multiplied by an m by n matrix. Let us say Aij is the typical element of A. So C1 plus C2 multiplied by Aij of m by n order matrix. This comes out to be C1 plus C2 multiplied by Aij. So it is multiplied with each and every element of the matrix. So it is C1 Aij plus C2 Aij, because these are simply numbers, so they are distributive, and then you can again collect the elements and will have C1 Aij m by n plus C2 Aij m by n, and this simply means C1a plus C2a. So what we have is C1 plus C2a is equal to C1a plus C2a. That means A6 also holds for this set. The next property is distributive property. So let us see C1 C2, two scalars multiplied by A. So it is C1 C2 multiplied by a typical element of the matrix. I am not writing m by n here again and again. So but this simply means the Aijth element of the m by n matrix. So it is C1 C2 Aij, it's multiplied with each and every element of the matrix, and then this product, this is simply a number, so they can be distributive. You can put the you can interchange the brackets, and finally what we have is C1 C2 into A. So this property also holds for scalars and matrices of order m by n. Next and the last is the existence of identity. So 1 belongs to set of real numbers. So 1 is a scalar which when multiplied by an m by n matrix A will not affect the matrix, and what we have finally is A. So 1 multiplied by each and every element of the m by nth order matrix will not change any element here. So what we have is simply A. So all the properties are satisfied, and one can say that the set of all m by n matrices forms a vector space. Now these are some of the examples which we are they are simple examples, we are aware of them, but let us take an example which is slightly different than what we had so far. So now we defined a vector V consisting of all real numbers belonging to R, and here I am defining the addition of two vectors in a different manner. So I am not using plus sign here because plus may be little bit confusing here, because here I mean to say the addition, by addition I mean to say actually the product of two vectors alpha and beta, alpha being defined as a real number. So alpha plus beta is equal to alpha beta product of alpha and beta, and C star alpha, by this I mean to say alpha raised to power the scalar C. So alpha is a real number and C star alpha means alpha raised to power C. Now my claim is then V plus the operation of addition which I have defined in this particular manner, and scalar multiplication if I define in this particular manner, then it is also a vector space. Now to prove this, I have to first check that this operation is closed or not. So for this I consider two vectors alpha and beta, they belong to V, but what is V? V is actually a subset of real numbers. The way I have defined this, V is a subset of R and alpha beta belongs to V. Now when alpha beta belongs to V, then this product means alpha beta that also belongs to V, because multiplication of two real numbers is also a real number. So this is also closed. Star is also closed as alpha raised to power C, alpha is a real number raised to power a real number C also belongs to V. So plus is closed as well as star is closed. Next is the commutative property. So alpha plus beta is equal to alpha beta. which is equal to beta alpha, because these are numbers, they can be commutative, and this is nothing but beta plus alpha. The next property is associative. So we will say alpha plus beta plus gamma is equal to alpha beta gamma is equal to alpha beta gamma. These are now numbers, so they can be associative and they can be written in this form. So this becomes associative property. So next is additive identity. It is 1. So alpha plus 1 is equal to alpha multiplied by 1, because the way I have defined this operation, it is the product of the two. So this alpha into 1 real number multiplied by 1 is the same real number alpha. So this is additive identity. Additive inverse, in this case, if I have alpha belonging to V, then there exists 1 by alpha in V, such that when they are multiplied together, what I have is additive identity. In this case, additive identity is 1. So alpha multiplied by 1 by alpha is equal to 1. So we can say additive inverse of alpha is nothing but 1 by alpha. So that is how we define additive inverse. Next thing is the distributive property. Now to check the distributive property, we will have C star alpha plus beta is equal to, this operation is alpha beta. C star, this means alpha beta raised to power C, and these are simply numbers. So I can write down this number as alpha raised to power C, beta raised to power C, or we can say if this is the product, then I can say alpha raised to power C added this operation beta C. So these are product of the two, and alpha C is nothing but C star alpha plus C star beta. So C star alpha plus beta is nothing but C star alpha plus C star beta. So we have proved the distributive property. Alpha C2 into C1 can be written as alpha C2 C1, and this simply means that C1 C2 star alpha is the same as C1 star C2 star alpha. So that proves the A6, the associative property. Finally, the A7 is C1 plus C2 star alpha is equal to alpha times alpha raised to power C1 plus C2. This is a scalar, so it is C1 plus C2, and this can be written as alpha C1 multiplied by alpha C2. This is the property of real numbers. So we can say alpha C1 plus alpha C2. So we can, this is the product of two numbers, alpha C1 into alpha C2. So we can say alpha C1 plus alpha C2. So this is equal to C1 star alpha. This is nothing but C1 star alpha, and this is nothing but C2 star alpha, and that proves the result that C1 plus C2 star alpha is equal to C1 star alpha plus C2 star alpha. And with this we come to the last property, that there exists one belonging to V, such that one belonging to the set of real numbers, such that 1 multiplied by alpha is equal to alpha times 1, or it is alpha. So there exists a scalar 1 such that 1 alpha is equal to alpha 1 is equal to alpha. Thus, with the given operations, V is a vector space. So we have defined operations in slightly different manner, but still we could prove that this given set V is a vector space with respect to defined operations. Now, so far we have taken examples which are actually vector spaces, but in this example we are defining a set V of all vectors alpha such that alpha belongs to R and alpha is a positive number. Then we say that it is not a vector space with respect to the operations which we have just defined. Alpha plus beta is equal to alpha plus beta, and C star alpha is equal to C into alpha. Now the proof is, to prove this, what we have to do is we have to show that at least one of the axioms fails in this case. So we have to check all the axioms, and if there exists an axiom which is not satisfied, then we can say that this set is not a vector space. So we start with addition. So addition is closed because if alpha belongs to R, then alpha plus beta will also belongs to R. Alpha is a positive number, beta is a positive number, add the two, it is a positive number. So it is closed. It is commutative because alpha is a real number, so alpha plus beta is also a real number, so it is commutative. Similarly, to prove that it is an associative, addition is associative in this case, that is also satisfied. But when it comes to scalar multiplication, so if we take R, a scalar which is negative, then R alpha is also negative. So if alpha is a vector, R is a negative scalar, then R into alpha by this definition is a negative number, and this negative number because of this property will not belong to V. So we can say that this multiplication is not closed. So when this one property fails here, so it is not a vector space. So we can say that scalar multiplication is not closed, so this will not form a vector space. In fact, the proof is done, but still we can say that theta is equal to 0 is the additive identity, absolutely no problem. But minus alpha is the additive inverse of alpha, that's true, but minus alpha will not belong to V. So for given alpha, additive inverse will not exist. So this is another property which fails in this case, or we say that in this particular example V is not a vector space. You can check other properties, but the solution is complete because we have proved it is not a vector space. Another example, we have a set V consisting of R3, vectors in R3, x, y and z is equal to 0, x and y belongs to R with usual vector addition in R3, and scalar multiplication is a vector space. So this set with usual vector addition and scalar multiplication is a vector space. Now to prove this, one can check that addition and scalar multiplication, they are closed. Addition is commutative and associative, this one can very easily prove. I leave this an exercise for the viewers. Then we can say that 0 0 0 is additive identity for the set V. Further, minus x minus y 0 is the additive inverse of x y 0 for any vector belonging to V in this particular form. One can very easily check that when we add the two, it is the additive identity 0. Distributive property is also satisfied. Then we can talk about the scalar 1 such that 1 into alpha is equal to alpha, and all these properties proves that V is a vector space with specified operations. But if we slightly modify this set V as x, y, comma c, where c belongs to R but it is not 0, c is not 0, then it is not a vector space with usual operations. So slightly you make a change in this and it will not be a vector space, like the additive inverse 0 comma 0 comma 0 does not exist in V. So this is one property which says that V is not a vector space. This does not belong to V, because if it has to belong to V, then this must be C, and C is not 0, so C is not 0, so 0 0 0 cannot belong to V. So this is because of this reason we can say that x, y, c is not a vector space with usual operations. Another example which is not a vector space. Now we take an example where we have x, y if they belong to R. So this is a pair x, y, they belong to R, so it's a R2 with the usual vector addition plus and scalar multiplication defined as c star x y is equal to cx comma y. Now we are defining this scalar multiplication in a slightly different manner. See, earlier we are taking c star x comma y as cx comma cy. Now I have changed the meaning of scalar multiplication here. It is c star x comma y is simply cx comma y, and that means then V plus a star is not a vector space. One can prove it very easily. you can check C1 plus C2 star x comma y is equal to C1 plus C2x comma y. So this is only first component is being multiplied by this, so it becomes C1x plus C2x y, and now we can say C1xy plus C2xy. If I take the right hand side for this, I'll have C1x comma y plus C2x plus y, and that simply means the vector addition means C1x plus C2x plus y, that makes 2y. That means this is not equal to this, so it is not distributive. So with this scalar multiplication, the same set which we have taken earlier will not form a vector space. So it is important how the way you define the two operations. It's not, it depends upon the set V, it also depends upon the operations which you defined on them. So with this operation, the same set V will not form a vector space. Again, I will take an example of matrices. So if we have a set of n by n square matrices, but these square matrices are non-singular matrices, with usual matrix addition and scalar multiplication is not a vector space. We have proved that set V of m by n square matrices with usual matrix addition and scalar multiplication is a vector space, but when it comes to square matrices with usual matrix addition and scalar multiplication, then it is not a vector space. And the reason is the additive identity is the null matrix. We have proved that additive null matrix is the additive identity, but this additive identity is the null matrix which is not a non-singular matrix. Null matrix has determinant 0 and it becomes non-singular, it becomes a singular matrix. So null matrix does not belong to this set of n by n square non-singular matrices, and that's the reason that this will not form a vector space. So while m by n matrices, they form a vector space, but when it comes to n by n square non-singular matrices, they do not form a vector space. So V is not a vector space. Now we talk about some simple results which will hold for all the vector spaces irrespective of the set V, irrespective of the operations which we define. The first result is that there exists only one additive identity in a vector space. By this I mean to say that if we have a vector space, then there exists only one additive identity. You cannot have two additive identities in a given vector space, whatever be the vector space, whatever be the operations. Now to prove this, we prove it by contradiction. By this I mean to say, we assume that there are two distinct additive identities, theta 1 and theta 2. So by this I mean to say that theta 1 plus theta 2 is equal to theta 1, because theta 2 is additive identity. So when additive identity is added into theta 1, we will have theta 1. But theta 1 is also an additive identity, so theta 2 plus theta 1 being additive identity, when added into theta 2 it will not change theta 2, so theta 2 plus theta 1 is equal to theta 2 when theta 1 is being considered as additive identity. And by this I mean to say theta 1 plus theta 2 is equal to theta 2 plus theta 1, and this means theta 1 is equal to theta 2. So this means theta 1 is equal to theta 2. Theta 1 plus theta 2 is equal to theta 2 plus theta 1. Why? Because it is commutative. So they are equal. That means this is equal to this. Theta 1 is equal to theta 2. So what we have started with? We have started with two different additive identities, theta 1 and theta 2. They are not equal, but finally we have proved that they are equal. So it is not possible that a vector space has two distinct additive identities. Even if we start with different, we finally arrive at the same values. So by contradiction we have proved that there exists only one additive identity in a vector space. Now the next result says that there exists only one additive inverse for given alpha in V. So any member alpha in V cannot have two different inverses. So again we prove this result by contradiction. So let us say alpha 1 and alpha 2 are two distinct inverses of alpha in V. So there are two different inverses, alpha 1 and alpha 2. So since alpha 1 is the inverse of alpha, so alpha plus alpha 1 is equal to theta by definition of inverse. Similarly, alpha plus alpha 2 is also theta because of definition of inverse. Now to prove, we'll actually prove that although we have started with different values of alpha 1 and alpha 2, but finally we'll prove that alpha 1 is equal to alpha 2. Now to prove this, what we have done is, in the first I have added alpha 2. So alpha 1 plus alpha 2 is equal to theta plus alpha 2. I have added alpha 2 in this. But what is theta plus alpha 2? Is nothing but alpha 2, because theta is the additive identity. Now in this I'll add alpha 1. So alpha plus alpha 2 plus alpha 1 is equal to theta plus alpha 1. Theta plus alpha 1 is alpha 1. But what is this? Alpha plus alpha 1 plus alpha 2 is equal to alpha 2. So if I start with this, alpha 2 is equal to alpha plus alpha 1 plus alpha 2. But since this addition is associative, so I can write down this as alpha plus alpha 1 plus alpha 2. That means I can change the brackets like this. But then this addition is commutative, so I can change the order. So it is alpha plus alpha 2 plus alpha 1. And again I can change this bracket because of associative property. So what I have is alpha plus alpha 2 plus alpha 1, but then I have already proved that this is nothing but alpha 1. So I have started with alpha 2 and I have arrived at alpha 1. What does it mean? It means alpha 2 is equal to alpha 1, but this is a contradiction. That simply means it is not possible to have two different additive inverses for a given element in V, and that means inverse of a given alpha in V is unique. So for a vector space, we will have a unique inverse for a given vector. Now the next result says that if V is a vector space, then 0 multiplied by alpha is equal to 0 for every alpha in V and scalar 0, and C multiplied by 0 is equal to 0 for any scalar C and 0 in V. Now one thing is to be observed here, that this 0 and this 0, they are different. This 0 is a scalar. When multiplied by alpha vector, then result is a vector. So this 0 is a 0 vector, and in this case this is a 0 vector and this is also a 0 vector. Now to prove this, we start with the first one, 0 multiplied by 0. Now this I write it as 0 plus 0 multiplied by alpha. There is absolutely no problem because 0 is a scalar quantity. So 0 plus 0 is a scalar, still 0. So 0 plus 0 alpha is equal to 0 alpha plus 0 alpha. Why? Because this is distributive. Because the vector space, so this distributive property is satisfied. Now adding both sides, minus 0 times alpha. So if I add this, so 0 alpha plus minus 0 alpha is equal to 0 alpha plus 0 alpha, this is what I had, plus minus 0 alpha, this I have added on the both sides. Now the left hand side is simplified as this, because 0 is a scalar which you can take it outside. So 0 multiplied by alpha plus minus alpha is equal to 0 alpha, and then I have the distributive property, so I apply distributive property here, and what I have is 0 on the left hand side, on the right hand side will have 0 alpha. So I have proved that 0 is equal to 0 alpha. So the first part has been proved. This is true for any scalar 0 in any vector alpha. Now for the second part, the proof goes like this. I start with C0, 0 is a vector now, is equal to C multiplied by 0 plus 0, 0 being the additive identity, so 0 plus 0 is also 0. So C0 is C dot 0 plus 0. This dot represents scalar multiplication. So this can be written as C dot 0 plus C dot 0. Distributive property is applied. Now adding both sides, minus C times 0. Again the same way, this can be taken together on the left hand side, then it is 0, and then you can again apply the associative property on the right hand side. So this proves that 0 is equal to C dot 0, and that proves the second part of the result. Now the fourth result says that if V is a vector space and C dot alpha is equal to 0, then C is equal to 0 or alpha is equal to 0. So whenever C alpha is 0, then one of the two things must happen, either the scalar is 0 or the vector is the null vector. To prove this, we first consider that C is not 0. With this, we will prove that alpha is equal to 0. So C is not 0 but C alpha is 0, then I can multiply this quantity by 1 by C. So 1 by C into C alpha is 1 into, I am multiplying 1 by C on both the sides. So 1 by C into 0 is, because 1 by C is possible because C is not 0. That is why I have taken C not 0. So I am multiplying 1 by C on both the sides. 1 by C into C alpha is equal to 1 by C into 0. So right hand side is 0, but this side is 1 into alpha, but we know 1 is a vector space, so 1 dot alpha is equal to alpha. So this proves alpha is equal to 0. Now to prove the other part, we consider alpha not 0, and by adding minus C alpha on both sides and proceeding in this particular manner, we can prove that C is equal to 0. That establishes this result. Towards the end of the lecture, I will give few exercises. The viewers are advised to go through these exercises. They actually give some important results related to vector spaces. The exercise 1 says that if V is a vector space, then minus 1 into alpha is equal to minus alpha for every alpha in V. While the second exercise says that if U, V, W belong to a vector space V such that U plus V is equal to U plus W, then V is equal to W. So it is actually a cancellation law. U and W can cancel out and we can have V is equal to W. So to prove this, you simply have to add minus U on both sides and apply associative property. The third exercise is that if alpha is not 0 and A alpha is equal to B alpha, then A is equal to B. So this is again a cancellation property where you can add the two, where you can cancel the two scalars. Now to prove this, you have to simply add minus B alpha on both the sides and apply the results which we have already discussed. So viewers, today we have discussed vector spaces. I have started with definition of vector spaces. I have given some examples where we have defined the vector space, vector V, we defined operations, addition and multiplication, and we have seen whether a given V plus star is a vector space or not. We have taken some examples where it forms a vector space, and we have illustrated in few examples where the given set with given operations, they do not form a vector space. Thank you.